We'll go from the current slide. And I guess we're ready to go. Do you have any questions? Have you been able to keep up with things on YouTube videos?
Yes, sir.
You have. Great. Okay. Did you get the second test? I think you were there that day to get it. Maybe or maybe not. I don't remember.
Yes, I have it.
You have it. Good. I knew I emailed it, but I couldn't, or sent it through Blackboard. Okay. Here's the thing. I think I'm okay to say this now because I believe the chancellor came out with this. I guess you know we're not going back on campus this spring. Did you hear that?
Yes.
You did?
Yes.
Okay. Where did you hear it?
I've just been keeping up with the news and keeping up with Boston State's website.
Oh, okay, good. I didn't know if they had it on there. Super. Okay. So we're going to be like this for the rest of the term. Are you okay with it?
Yes.
Okay. Now, I'm just guessing, because all I see is your name, that you don't have a camera, or do you?
I do.
You do. But I don't need to see you. I know you probably don't want to see me, but it doesn't matter to me. But I just was wondering if that was something. But anyway, I sort of was killing time hoping someone else was going to log on, but since they haven't, let's go on and get started. Did you see the last YouTube video?
I did, yes.
Okay, I think we finished right at 4.1. That was so long ago I'm having trouble, but it's where my mark was in my book, so I assume that's where we are. Are you okay with that? Is that where you were thinking we were too?
Yes.
Okay. Well, Chapter 4 is still application. Do you have any questions on anything then?
Right now, no.
Okay, super. All right. Well, we're still in Chapter 4, applications of differentiation. And 4.2, let me see if I can move this and get this. I don't know if it's in your way, but it's in my way. Could you tell I did anything? I just moved my little box. Oh, JJ's here. Okay. Welcome, JJ. Can you hear us yet? I see you even. And you're connecting to audio, so I don't know if you can hear me yet. Can you? Still coming on. Carlos, can you tell us that JJ is here?
Yes, I can see. I can tell.
Okay, super. All right, JJ, you hear us yet? Oh, he's putting in his ears. Okay. Can you hear us, JJ? Not yet. Can you see me? I can't give any indication. Hey, JJ. Oh, he's still connecting. All right, there he is. All right, are you in? Can you hear me, JJ? Okay. I can just barely hear you, but that's fine. All right, we're just getting started. Carlos is here. I guess you can tell that too. And we finished 4.1 last time. JJ, you were here last time, right? Yeah. And we're starting 4.2 today. And this is Rolle's theorem and the mean value theorem. And one of the reasons I was asking this, I thought we just went over the mean value theorem, but then I realized that's probably my 212 class, 227 class when we're doing it in 3 dimensions. So I get confused easily. Okay. So anyway, that's where we're starting today. JJ, do you have any questions at all? All right. I got your second test, and I've already got the score out on Blackboard if you check. Okay. Way to go. The other thing, JJ, I don't know if you had heard this or not. Carlos had. We're doing this for the rest of spring. Yeah. Okay. I think I had told y'all I didn't think we were coming back in the anymore, and definitely we're not.
Even if the rest of the classes did, that you'd still be doing the online thing. So
yeah, right. Everything is going to be this way. All right, so we're continuing. Do you have any questions before we get started? No. Okay. So we're talking about Rolle's theorem and the mean value theorem. Okay. Just a little bit of review, not a lot, but remember what we were doing last time. we were looking at finding extrema, okay? That's minima, maxima on open intervals and closed intervals. On open intervals, they're often called relative maxima or minima, but on the closed interval, which the endpoints are included, then we talk about absolute maximum or minimum. And you could talk about the relative in between. So here, building on that is Rolle's theorem, and then later the mean value theorem. Our objectives here are to understand and use Rolle's theorem and to understand and use the mean value theorem. All pretty creative, aren't they? All right, so Rolle's theorem. The extreme value theorem that we did in the last section states that and this is so aggravating, my box is right in the way of reading this. Let me move everybody down here for a moment. I don't know if that makes any change to you, but anyway. Oh, it reorganizes things. All right. Now, oh, here is Joanne, right? Joanne, can you hear us yet?
I can hear you. Can you hear me?
Yes, I can. Okay, and Carlos, yeah, I think you went muted and then you unmuted. Are you okay?
Yeah.
Okay. All right, good. Let me see if I can arrange the boxes a little bit more. Okay. Everything changes when I make a little change. Well, oh, Kyle's here. All right. Can you hear us yet, Kyle?
Yeah, I can.
Excellent. I can't hear you well, but I could hear you. Welcome to the class. Okay. I'm losing some videos, but y'all probably are trying to lose my video. Okay, I got it. All right. We have already started, and before we get too far again, I'll ask this question every time someone new comes on. I guess everyone's gotten the word that we are doing online for the rest of spring. Was that a surprise to anybody? You still there? Anyone? Okay.
It was not a surprise.
Okay. All right. I was hoping it wouldn't be. I've been saying it all along, but that doesn't mean anything. But yeah. All right. So let's continue. We're in Rolle's theorem. This is chapter 4, applications of differentiation, section 4.2, Rolle's theorem and the mean value theorem. Right now we're talking about Rolle's theorem. And in 4.1 we had what was called, I'm trying to find the page number for you here, back on page 209, no, that's not it, 206, the extreme value theorem, okay? Back on page 206 in 4.1, right at the first page in 4.1, stated that a continuous function on a closed interval a to b must have both a minimum and a maximum on that interval, somewhere on that interval. It may have more than one, but it will always have one. Both of those values, however, could occur at the endpoints. That's what the issue with the closed intervals are. Rolle's theorem, on the other hand, is named after French mathematician Michel Rolle. I'm not even sure I'm pronouncing his name right. It may be Rolle. They don't put the symbol, the accent aigu, the acute symbol over the E, so I don't know how you pronounce it. But he gave conditions that guaranteed the existence of an extreme value in the interior of a closed interval. So why don't they call it an open interval? Because that's what the interior of a closed interval is. I'll have to move your block, and that might not make any difference here. Up here to the top now. And here's Rolle's theorem. Theorem 4.3. If let f be a continuous function, got to be continuous. You cannot have, this theorem makes no sense if you have discontinuities, because you might hit a discontinuity and it blows it all off. So if f is a continuous function on some closed interval a to b, and is differentiable on the open interval a to b. Now, if f of a is equal to f of b, in other words, at the endpoints you have the same values, then there has to be some number, c, somewhere between a and b, such that f prime of c is equal to 0. Okay? F has to be a continuous function on a closed interval and differentiable on the entire... Oh, Jonah's here. Okay. I didn't see that. Jonah, can you hear us yet? Not yet. Still getting set up. Has anyone else joined the class since, Jonah, you haven't heard me acknowledge your name?
I'm here. I just got here.
Okay, good morning. All right.
I was looking on Blackboard for the under the announcements, but it wasn't there, so I just kept looking, and then I found it on the other spot.
Wow. Did any of the rest of you have trouble finding on Blackboard?
Yeah, I did. I thought it would be under announcements too, but I just started looking around and found it.
Huh. I posted it last evening, and you say on Blackboard it's not under announcements.
It's under messages.
Oh,
Class.
okay. I thought that was announcements on this new Blackboard. Okay, sorry about that. That's where I'm going to be communicating, is through messages. Is that okay?
Yeah.
Okay. Cal, were you going to say something? Okay. All right. All right, we're in, and by the way, Jonah, and if any of the others came in after I said this last time, I guess everyone's gotten the word, haven't you, that we are not going back to campus this spring. It's going to remain this way for the rest of spring term. Is that causing...
I got that message.
Okay, good. I figured that kind of word gets around pretty quickly. Okay. I was a little hesitant because when I received the message over the weekend, I was told, now don't tell anyone this. It said don't tell any staff this because the president's going to make his announcement, blah, blah, blah. So I didn't know. That's why I asked, have y'all heard this yet? Because I found out last night that the chancellor had come out with it. Say again?
They never sent out an official announcement, but then you got the email that, about choosing an alternate graduation. So it's like, okay, well, I kind of guess from here that we're not going back.
Right, right. And my wife's a infectious disease epidemiologist, and she's been following the numbers, and she said April's going to be our worst month yet. So I could not imagine that we'd be going back to campus. So, yeah, you got it. Okay. So where were we? Talking about Rolle's theorem. Any questions before we get started? Because I know some new people have come on. All right. So if you have a continuous function, that means there's no gaps, no holes, nothing missing in closed interval a to b, and it's differentiable everywhere on that open interval from a to b. Doesn't have to be differentiable at the endpoints. It's sort of hard to be that because you don't have differentiability from both sides because you don't know what's on the other side of a or b, just from one side. But if f of a is equal to f of b, then there's got to be at least one number c on that interval such that f prime of c is equal to 0. That means the first derivative is 0, meaning you have 0 slope for the curve at that point c. Okay? Now, if f of a is equal to f of b, they're at the same value there. If that's just a straight horizontal line going from f of a to f of b, f prime of c is 0 at every point. So c would be any point in between a and b. But if f does start off from a and start going up, it's got to come back down to be back at the same value of b, f of b. Does that make sense? So therefore, it's got to change direction somewhere there there your first derivative would be 0. Well, you might say, well, could it be a cusp or a corner there? No, it couldn't, because it's differentiable on that open interval. If it's differentiable, that means it's smooth and continuous. So if it's a smooth function, starts out going up from f of a, it's got to come back down because f of a is equal to f of b, and at that point where it changes direction, there the first derivative will be 0. If it starts off going down from f of a, heading downward, it's got to come back up to reach the same value of f of b, so there's got to be some place it turns, and it has to be smooth and continuous. Does that make sense?
Yes.
Okay. Blah, blah, blah. I can hear it. Okay. Now, from Rolle's theorem, you can see that if a function f is continuous on a to b, yep, differentiable on a to b. Now, I've got my hands up here. I don't know if you can see them. The square brackets are the closed interval. The rounded hands, those are the open interval. And if f of a is equal to f of b, there must be at least one value, x value, in between a and b, they were calling it c, at which the graph of f has a horizontal tangent, as shown here. Here, let me get my pen out. Okay, I'll actually change my color here. And by the way, I want to ask y'all to always make sure that I'm recording. I'm trying to remember to do that. I have to get Zoom started. I have to get the PowerPoint started. I have to get Screencast-O-Matic started, and sometimes I'll forget to do one of them. So I can't do the teach without the PowerPoint, so it's not going to be that one. It's probably going to be the Screencast-O-Matic, but we are recording. So here, f of a is this value d here. F of b is that same value d. And like I said, if the function takes off and increases from there, it has to turn around and come back down. And if this is a continuous function, it can't have a gap there. If it's a differentiable function, that means it has to be smooth there. And if it's smooth and continuous, you're going to have at least one turning point, and that happens in this case to be a relative maximum. Okay? Make sense? That's just restating the theorem. Now, is anything wrong with this picture? There we have a relative maximum. Does this fit Rolle's theorem? Yay or nay? Why not?
Because it's not smooth.
It's not differentiable there, because you see the derivative coming up here is going to getting very, very large positive, but then the derivative coming down on the other side of that relative maximum is extremely large negative and getting less negative as you go. So no, it's not differentiable at that point. So Rolle's theorem doesn't work on this one. That doesn't apply here, because the differentiability requirement, if that's dropped, you may have a critical number in a to b. Now, I want someone to remind me, what are the two conditions for a critical number? Oh, this is 2 weeks ago. That's a long time, isn't it? Two things we consider for our critical numbers. I call them critical values, but this book calls them critical numbers. Same meaning. All has to do with the first derivative. Hint. Either where, on this one, the first derivative is anybody. What's your first derivative there at your relative maximum? 0. Or, what's your first derivative at that relative maximum? It's a sort of a tricky question. It does not exist. Those are the two criteria to be a critical number, where the first derivative is 0 or where the first derivative does not exist. Rolle's theorem says if it's a continuous and differentiable function between a and b, you must have and has the same value f of a and f of b at the endpoints, then you've got to have a first derivative equal to 0. You cannot have the first derivative that doesn't exist, because then it wouldn't be differentiable. Okay. That okay?
Yes.
Beating that to death, aren't we? All right, here's example 1. It says find the two x-intercepts. Wait a minute, have we been talking about x-intercepts? It didn't seem like it. Of f of x is equal to x squared minus 3x plus 2. But we know how to do that, don't we? How do we find the x-intercepts? This is not a calculus question. This is a algebra question. How do you find the... What does it mean to be a x-intercept? Tell me something that's true about the x-intercept. Anybody? Y is equal to 0. And what's your y? F of x. So set this equal to 0. Now once you set it equal to 0, what is the next thing that pops in your head? Oh, don't tell me. But no, okay. What do you do next?
Solve for x.
How? Factor. Excellent. Okay, and how does this factor? If it factors. If it doesn't factor, what is our next step? Starts with quadratic. Formula, exactly. Okay, but let's see if this one will factor. If it does, what's the first only possible factorization for x squared? Help me, somebody. X times x. Then I always look at the sign of the last term. Okay, I'm what I call unfoiling. We did the first, now let's go to last, but only focus on the sign here. That sign is positive. What does that tell you about these two signs here? They have to be the same. So look at the middle sign to see what they've got to be. Any suggestions? Both negative, right. Okay, so the signs have to be negative. Now, what's the only possible factorization for 2? Help me. 2 and 1, of course. And check it and see, FOIL it. X times x is x squared. Minus x minus 2x, that's minus 3x, that works. Plus 2, that works, okay? Yeah, we've got the factorization. So, what are the two x-intercepts? Okay, did I hear x equal 1? Say yes. All right. Or, what else? Anybody? X equal 2. Okay? So what have we got here? We've got two places where the y value, f of x, is the same, is 0 at both of those places. X equal 1, x equal 2. What does Rolle's theorem tell? Okay, number 1, is this a continuous function? Yay or nay? Yes. Okay. Is it a differentiable function in between 1 and 2? Yay or nay? Help me. Hey, polynomial functions are always differentiable. So yes, that's differentiable. Anywhere, not just between 1 and 2, but it is differentiable between 1 and 2. Okay? I don't know how to answer this or ask this question well. I have a little symbol by Kyle's box that indicates no sound. Does that mean I can't hear you or you can't hear me? But if either one of those are the case, I don't know how you answer it. Kyle, it went off.
That just means I can't hear you. I just don't want any background noise.
Oh, I see. Like my talking. I see. Got it. Oh, okay. I got it.
They can still hear you.
Okay.
You just can't hear whatever's going on there.
Okay.
My dad's doing like we're renovating our house. So
Oh, I see. Yeah. Sometime this morning we're going to have our driveway repaired. We had a tree go down and broke up a portion of the driveway, so we're going to have background noise as well. I just heard a bling. Did somebody else come on board? I don't see a name yet. Okay. All right. So we need to show that f prime of x has a 0 at some point between these two intercepts. Guess what? We just did it. Because we showed that number one, f of x is a continuous function. Polynomial functions are always continuous. We also showed that this function is differentiable between x equal 1 and x equal 2. It's differentiable everywhere because polynomial functions are differentiable everywhere. And we have two values for x, 1 and 2, that have the same y value, specifically 0. So therefore, we've satisfied everything in Rolle's theorem. That means there indeed is some value x in between 1 and 2 that has a first derivative of 0. Now, the next question is, how could we find it? We've done what the problem said. We found the two intercepts. There they are. We've shown by Rolle's theorem that it does have f prime equals 0 some point in between the two. How do we find that? What's our next step? The Jesus answer in this course. Take a derivative. So what's f prime of x? Anybody? 2x minus 3. Okay? And then what are we going to do? Can you see what I'm circling? We're going to set it equal to 0. Excellent. And let's solve that equation. That's a pretty easy one, isn't it? What would that give us? Anybody? Do the steps or just tell me the answer. I don't care which.
x equals 3 over 2.
X equal 3 halves. Perfect. Okay? 3 over 2, 1.5, however you want to say it. We knew that anyway, didn't we? Because we knew that quadratic functions are always graphed as a parabola. We have these two values being the same. Parabola are always symmetric about the axis of symmetry. And so therefore, if symmetric, there's 0 here and there. They have to be 0. The first derivative would have to have a maximum min exactly halfway between 1 and 2, which is 1.5. So we have gone beyond what they asked for. We actually found that point in between 1 and 2 where the first derivative was 0. Let's see how they did it. Any questions so far? Note that f is differentiable. We noted that on the entire real number line, and it was, and it is. It's also continuous on the entire real number line. We set f of x equals 0 so we could find the zeros of the function, and that gave us x equal 1. We factored it, x equal 1 and x equal 2. So now we've met every criteria for Rolle's theorem. It's continuous on the closed interval between 1 and 2. It's differentiable on the open interval between 1 and 2, even though it's differentiable beyond that and continuous beyond that. Okay, so we have at x equal 1 and x equal 2, the function has the same value, 0. Okay, so there has to be a point in between. So f of 1 equals f of 2, that's equal to 0. From Rolle's theorem, you know there has to exist at least one c in the interval 1 to 2 such that f prime of c is equal to 0. We've shown it. Rolle's theorem, to find it, take a derivative. 2x minus 3, determine that's equal to 0 when x is equal to 3 halves. Perfect. Any questions? Here's the actual picture of it. And we could have told you this too, right? Because the leading term is positive. That means it's opening upward, and therefore your parabola is opening like that. The axis of symmetry has to be exactly in between those 2 points because it has to be, those 2 points has to be equal distance between them. That puts it 1.5. That's a minimum. Does that make sense? Any questions? All right. They are skipping example 2. So let's us go back and do 2. Let f of x equal x to the 4th minus 2x squared. It says find all the values c on the interval -2 to 2. I can't write. Oops. Open interval. Lost it. There it is. Such that, colon means such that you saw, okay, no, f prime of c is equal to 0. Okay. You know what? Doesn't look like to me you need Rolle's theorem at all on this, do you? But it's indeed there. The first derivative is 0. The function is continuous. First derivative is continuous. Exists everywhere between -2 and 2. The only thing we don't know right now is f of -2 equal to f of +2. Anyone want to make a weight? No, we won't do that. Suggest whether that's equal or not. I know that's a pretty vague question, right? I can see right now all the confusion on your faces. No, I see sleep. No, I don't see that. Okay. What do you know about this function here? Anyone want to suggest a description of that function? Please, somebody say something. What kind of function is it? Yes. Saw Carlos. It's a polynomial. It certainly is. A little more specific.
On a graph, it would be a circle.
No, not quite. I think I sort of see what you're talking about, but that wouldn't even be that. Okay, I'll make it a multiple choice. Is that okay? Because you probably don't know what I'm looking for. Is it even or odd? Uh-oh. Why do you say odd? And it could be a neither too. Even, I should have said multiple choice. Even, odd, or neither. Anyone remember? Hint. Say that again.
I said I remember judging the graphs, not the equations.
Okay, that refers to the graph, if that's what you're saying. My hearing's terrible. Huh? It's an even function. Why do you say that?
Because when it's graphed out, it's symmetrical across the y-axis.
Okay, that is a definition for an even function. With polynomial functions, there's a really easy way to look at it and tell without graphing it. Did you graph it on your graphing calculator or something?
I use my graphing calculator.
Yes, so yeah, and that certainly gives that. Just looking at the function without graphing it, what do you notice about the exponents?
They're both.
Both what? Even. That makes it an even polynomial function. That doesn't work with every function, but it works for polynomials. If both of those were odd, it would be an odd function. If they were mixed, it would be a neither function. So this is an even function. So what Jonah just said, that means that it's the same on either side. So we know that f of minus 2 has to equal f of 2, right? So now Rolle's theorem does work. So we know there's got to be at least one c in between minus 2 and 2 for which f prime is equal to 0. How do we find them? Come on now, this is the easy question. What's the Jesus answer? Take a derivative. F prime of x is 4x cubed minus 4x. Perfect. What do we do with that? What do we do with that? Set it equal to 0. And then what do we do with that? What's the F word? Factor it. How does that factor? 4x times x squared minus 1 equals 0. Are we through factoring? Yay or nay? I feel like a dentist here. Pulling teeth. Does this factor any further? Difference of two perfect squares? Help me, somebody. We have to remember algebra in this course. What does that give us? X plus 1 times x minus 1. Perfect. All right, now we got 3 factors. And by the way, that's the most number of zeros you can have is 3. What are those 3 zeros? Okay, this gave us a minus 1, this gave us a 1, this gives us a 0. So x equals 0, x equals minus 1, and x equals 1. Now I'm not going through and setting each of those equal to 0. Y'all know how to do that, right? Or would it be helpful for me to do it, to remind you? You know what we did there? The product of these 3 numbers is zeros. That means either 4x is equal to 0, or x plus 1 is equal to 0, or x minus 1 is equal to 0. If a product of any number of numbers comes out 0, one of them's got to be 0. You can't get any other combination of numbers multiplying together to give you 0 unless one of them is 0. And this, when you divide both sides by 4, this gives you x equals 0. When you subtract 1 from both sides, you get x equal minus 1. And when you add 1 to both sides, you get x equal plus 1. I was avoiding that. Should I have done that? Would that have made it easier to see? Yay or nay? Anyway, have we answered the question? Find all the values of c. So let's not call these x anymore. Let's call them c. There are all the values of c such that f prime of c is equal to 0. And all 3 of these are in that interval. So yes, we found them all. And Jonah had those on his graphing calculator too, didn't you?
Yes.
Yeah. Okay. So you could do it that way as well. But this way is algebraic, which of course is much more fun to do than an old graphing calculator. Okay. Any questions on that then? There is a technology pitfall given at the bottom of the page because they knew Jonah was going to do it on his graphing calculator. A graphing utility can be used to indicate whether the points on a graph in examples 1 and 2 are relative minima or relative maxima. But when you use a graphing utility, you have to keep in mind that it can give you misleading pictures of the graph. This graph they show here, their window is -3 to 6 on x and -3 to 3 on y. And you graph this function here, f of x equal 1 minus x minus 1 squared, minus, of course, one of my favorite functions of all time, 1 over 1,000 times x minus 1 to the 1/7 power plus 1. In most viewing windows, it appears that it only has a maximum of 1 when x is equal to 1. But if you had expanded your window a huge amount, you would find, and they don't show the rest of them here, let's see, it appears, you need to examine the graph analytically to get the complete picture, which that would be a bear and a half to do, because you would have to use, well, it's doable, but it would be a real pain. But it does have more than one zero, by the way. More than one max or min. Any questions on that? Let's move on to mean value theorem, page 216. Any questions so far? Okay, mean value theorem is basically going to be used to extend Rolle's theorem to prove another one. And this is a very useful, I want to say popular theorem in all of calculus, the mean value theorem. Here's what it says. If f is continuous on a closed interval a to b, that sounds just like Rolle's. Differentiable on the open interval a to b, sounds just like Rolle's. Then there exists a number c on the open interval a to b such that f prime of c, wait a minute, this is equal to, this almost looks like our, well, it's exactly our slope formula. F of b minus f of a, that's y2 minus y1 over x2 minus x1, isn't it? There is some number c, and notice here, we don't need to know beans about what the values are, f of a and f of b. Rolle's theorem, they had to be the same. Mean value theorem, doesn't matter. If they are any value, including the same, if they were the same, if f of a is equal to f of b, then what's your numerator there? 0. And that's exactly what we had before. F prime of c is equal to 0 at some value c in the interval. That was Rolle's theorem. But the mean value theorem says whatever their values are, f of b minus f of a, the f prime of c is going to be f of b minus f of a over b minus a. In other words, whatever the slope is between those 2 points, you're going to have some value of the function that's going to have a slope exactly the same as the slope between the endpoints. Okay? That's the mean value theorem. Now, that doesn't seem all that exotic or special, but it's used a lot. So here's example 3. And excuse me. Before we get to example 3, there was a little blurb here on Joseph Louis Lagrange. Okay, born in Italy. It sounds like a very French name to me, but he held a position in the court of Frederick the Great in Berlin. I don't know if y'all remember who Frederick the Great was, or how great he was, or anything. He was one of the Holy Roman Emperors. And I can remember my senior English teacher, I don't know why she was talking about it, but she was. She said, yeah, the Holy Roman Empire, it was neither holy nor Roman nor an empire, okay? But Frederick the Great was a great Holy Roman Emperor that basically was sort of like the Germans of today. He was headquartered in Berlin. But anyway, Lagrange went to his court and was basically a court mathematician and probably did other things as well. Pretty famous mathematician. There's Lagrangians you'll run into in physics and other courses. And while I'm on, why am I mentioning this anyway? Oh, it was because I happened to notice, just happened to notice, that this, one of my best classes ever of all time, how many research papers have I got in? Oh, 0. Not a single one yet, okay? We've hit Rolls so far. We've hit Lagrange, Rolls theorem, mean value theorem. There's a lot of potential paper topics. There are 4 right here in this one little section. Folks, please don't forget to do your research paper. Just because we're not coming back to campus doesn't mean there's not a research paper. Please do it. And while I'm on the subject, I don't know if I don't think he's on board yet, and I don't know if he's listening to the YouTube videos, but hopefully he is. There is one person, and just one, who has not turned in the first test. And he told me before we left campus he had it finished, but doesn't have it in. Those of you who have turned in things, let me remind everyone of how you do that. 2 possible ways. You can either scan it if you have a scanner, or you can take a picture of it if you have a smartphone. A Polaroid won't work, a smartphone picture. Okay, then you can send that file to me either one of 2 ways. You can send it through Blackboard, through the message, like you're used to now getting your messages about the class, or you can send it to me through email. I don't care which, either one. I'm trying to check them both every day. It's really hard because there's lots of stuff coming in now every day, but I'm trying to check them every day. So please, if you, and at least one person has turned in test 2 already, and the rest of you can turn those. But that one person who hasn't done test 1, please get that into me as well. And then all of you get your research papers in. And again, either scan them, that I would think, well, wait, one other way, I'm sorry. If you did your paper in Word, you can just email it to me in Word, or you can attach it in in the Blackboard. You can do that as a message, attach it there. You don't have to scan a Word document. You can just send me the Word document. I can print a Word document, okay? I can print lots of other kinds, but I figured those would be the easiest. The Word, PDF, which has got what you get when you scan, or your picture file, and that could be a PDF if you have a phone that will do that, or it could be JPEG and some of those other things. I think my computer will read all those. So far, I've been able to read them all. Okay, any questions on that? All right, here's example 3. And by the way, you can go to larsoncalculus.com for an interactive version of this type of an example. So here's your function. F of x is equal to 5 minus 4 over x. It says find all the values of c on the open interval from 1 to 4 such that f prime of c is equal to basically mean value theorem. Why they even put that in there? They should have just said, show that the mean value theorem works here. Now, question for you. Is this function continuous everywhere? Yay or nay?
Yes.
Multiple choice.
Yes.
Okay. Guess what? No. No. Okay, why? Can you picture or imagine a place where it's not continuous? Look at that second term. Oh, it's not continuous at 0. It's not even defined at 0. So it can't be continuous at 0. This is not a polynomial function, okay? They pulled the quick one on you here. So it's not continuous at 0, so it's certainly not differentiable at 0. But guess what? Our interval is 1 to 4. 0 is not included in that interval, so that could still meet the criteria for mean value theorem. So what we have to do then is find all the values of C in that open interval for which this is true. Okay? What is f of 4? Did someone say 4?
Yeah.
Very good. Okay, because 4 over 4 is 1. 5 minus 4 is 5 minus 1 is 4. Okay. What's f of 1? 1. Over? Which is? 3, right? And that is 3 over 3, which I think someone said 1. I already figured that out. Where the first derivative is 1. Well, we are guaranteed there is at least one value. Let's see if we can find it. What would we do to find it? Take a derivative. F prime of x is equal to what? I'm going to rewrite f of x if that's okay. Any of you want to make a guess of how I want to rewrite it? 5 minus, I'll even write the 4. Second? X to the minus 1. Perfect. That's much easier to take a derivative of it. What is the derivative of that? 4. Not quite 4. You're right that plus 4 is in that. What do we have to do? Second, subtract 1 from minus 1 and you get minus 2, which another way to write this is 4 over x squared. Now I've gone back to writing it the other way, okay? And what we want to do is set that equal to what? Trying to set it equal to f prime of c, which is this thing, 1. Do you see that? Where this derivative is no longer looking for where it's equal to 0, you're not going to find that. We want to find out where it's equal to mean value theorem, f of 4 minus f of 1 over 4 minus 1. Okay? So how do we find that? Anybody? Okay, did someone new come aboard? I saw something happen to my screen. Someone new in the classroom? Maybe someone left. Okay, I don't know. We wouldn't. They wouldn't do that. Okay. What would you do? How would you solve that equation? Help me, somebody. What's messy about that? The denominator. How do you get rid of the denominator? Don't erase it. If something's divided by something, how do you get rid of it? Multiply by that same thing. So multiply both sides by x squared. That gets rid of your denominator there. And what does that give you? X squared is equal to 4. And what could be possible solutions for that? X equal plus 2 or minus 2. But guess what? We're looking for values that are in this interval. Which one of them is there?
Plus 2.
So C is equal to 2. There we have it. Okay? So, We've done what it says. Find all values C on the open interval 1 to 4 such that your derivative of f is equal to the slope between the two endpoints, which happens to be slope of 1. C is equal to 2. Okay, I just heard a music go off here. Does that mean someone new is in the class? No one? Okay. Oh, I may be getting an email or something. I don't hope not. But anyway, never mind. Let me erase this. All right to erase? Let's see how they did the problem. The slope of the secant line, that's what it's called, the line that connects the two endpoints through 1f of 1 and 4f of 4 is 1. You found that with no problem. Okay? Note that the function satisfies the conditions of the mean value theorem. It's continuous everywhere, big point here, on this interval. Continuous everywhere on the interval and differentiable everywhere on that interval. Not continuous at x equals 0, not differentiable at x equals 0, but 0 is not in the interval. So it does satisfy the conditions of the mean value theorem. So it is continuous on that interval, differentiable on that interval, closed and open. So what we do then, there exists at least one number C, 1 to 4, such that f prime of C is equal to the slope of the secant line, 1. Well, how do we go about doing it? Take a derivative. And they didn't show how, but you knew how. That gave you 4 over x squared. And set that equal to 1, which is your slope of your secant line. That implies that x equals plus or minus 2. But guess what? Plus 2 is on this interval, minus 2 is not. So we found the one and only one value on that interval for which that is true. Okay. Now, interesting little graphic here. Here is this portion of the graph of the slope. I'll just tell you now, let's go back and see what the function is. There it is. 5 minus 4 over x. That would be, I believe, f of x equal 5 would be a horizontal asymptote. So let me, okay, I don't know what that other little thing was. So if you went up here to 5 here, you would have a mirror image over here that did something like, 5 and 1. Yeah, no, 5, okay. It would be something like this, okay? No, I got it wrong. Sorry about that. Okay. I believe it's like this. Okay. Going up just the same way, sort of a mirror image around the, I didn't draw mine well. The horizontal asymptote is x equals 5, I believe, and the vertical asymptote, of course, is x equals 0. Okay? But we're not worried about that side. There is another place over there at x equals minus 2 where it also has that same slope. But we're not worrying about that one. My picture isn't very good. But here is f of 1. Here's f of 4. There's a secant line that connects those two. Here, there is another place who has the same slope as that. Now, we didn't find the point, though, did we? Was that part of the question? No, only asked for all values of C. Now, if they did ask for at what point is this true, then what you do is, you know, x equals C, or C is or x equal 2, or C is equal to 2, plug that in here. F of 2 is equal to 5 minus 4 over 2, and what would that be? Anybody? 3. And that's where they get the point 4.23. 2 is the x value, 3 is the y value. Okay, and sure enough, the slope of the tangent line at that point is the same as the slope of the secant line here. I don't know why they colored pink in between. It makes it look like that's something important. It really isn't. They're just showing those two lines are parallel. Does that make sense?
Yes.
So there's mean value theorem. Does that give you any indication how you use this thing? Probably not, but it is an important theorem. All right. All right, to move on to example 4.
Yes.
Okay. Before we, got to find this in the book. Oh, they're skipping example 4. Okay. Let's back up here. And let's do example 4 here. Okay. Example 4. And of course you needed this one. 2 stationary patrol cars are equipped with radar and they're 5 miles apart on a highway, as shown in this figure. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. Okay? Got it? Okay? 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. It says, prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during that 4 minutes. Now, of course, what they want you to do is use mean value theorem. That's what we just did. But guess what, folks? You don't need to. Okay? That vehicle just went 5 miles in 4 minutes. What was its average speed if it's going 5 miles in 4 minutes? 5 miles in 5 minutes would have been, anyone guess? 60 miles per hour. 5 miles in 4 minutes? No way! He was going much faster on average at 60. So yeah, there's got to be at least one place. Okay? So to me, this is sort of a silly example, but you certainly can do it that way. But it's really a real big pain in the neck to do it. What you have to do, because you're dealing with miles per hour and feet per minute, miles per hour and so many minutes, you have to change your time to 4 minutes is 4/60th of an hour or 1/15th of an hour. So you have to do the position. It just is it's a ridiculous example of something really easy to do. But his average velocity, which is what I just said, was 5 miles in 4 minutes, is 75 miles per hour. So you don't have to do mean value theorem to get that. It's got to be going greater than 55 miles an hour many times in that interval. He just slowed down because he must have had a track. No, I wouldn't say that. All right. So I'll let you work that example if you need to. I'm sort of glad they skipped it on the PowerPoint. I must be getting emails like crazy. I hope none of them are students saying, I can't get on, how do I get on? Well, wait a minute. Yeah. This last slide in the section is at the bottom of page 217. And by the way, maybe the reason this is making all the noise no, we go until 11:40, right? Yeah, I was hoping we weren't running out of time. Okay. But y'all wouldn't let me do that, would you? Okay. Oh, yeah, that's right. Okay. A useful alternative for the mean value theorem is this. If f is continuous on the closed interval a to b, yep, differentiable on the open interval a to b. Got it? Then there exists a number c in a to b, the open interval a to b, such that all they do here is, remember how it looked before? It was alpha of b minus alpha of a over b minus a. That was equal to alpha prime of c. That was how mean value theorem was expressed before. All you do now is multiply both, because they don't like denominators either, both sides of the equation by b minus a, and then you get alpha of b minus alpha of a is equal to alpha prime of c times b minus a. Everybody got that, right? And then add alpha of a to both sides. And that gives you alpha of b is equal to alpha of a plus alpha prime of c times b minus a. Okay? That's how they get this alternative form. Now they put alpha prime of c at the end rather than at the beginning. I think why? Keep in mind that polynomial functions, rational functions, and transcendental functions are differentiable at all points. Now here's the key word here, in their domains. Okay? Rational functions are not differentiable where they don't exist. Okay? So that's why you can go, that last one was a rational function, did not exist at x equals 0. So therefore that x equals 0 is not in the domain, but it's differentiable everywhere else. And all your transcendental functions are. What are your transcendental functions? Well, your trig functions are. Sines and cosines are differentiable everywhere. However, the other four, they have those values, either the half pies or the whole pies or somewhere like that, where they're not defined, so therefore that's not in the domain. Okay? Your other transcendental functions are your exponential function, differentiable everywhere. Log functions, only differentiable where the argument is positive, greater than 0. Not at 0, not at anything negative. They don't exist there, so therefore they're not differentiable. Okay, so this will work for any of them. And this actually then is a more useful form, the alternative form here. If you're trying to find a value of a function, and you know at one endpoint what it is, and you know how far that endpoint is on the x-axis from it, and you can calculate the derivative, yeah, you can do that. So that's the alternative form. And that is the last element in slide in 4.2. Now on page 218, there's always the concept check at the top. A pretty good idea to go on and think through that anyway. You don't have to write it down or anything, but think through it. But then do homework exercises, either 3 or 5. They're both at calcchat.com. 7 or 9 are both at CalcChat, but 9's at CalcView. Any of the odds, 11 through 25, they're all at CalcChat. 13's at CalcView. And you get some of your transcendentals in there, your trig functions and exponential functions showing up down there toward the end of those. Excuse me, I got hiccups. Any of the odds, 27 to 31, they're all at CalcChat. 33 is at CalcChat. 35 is at CalcChat and CalcView. 37 or 39 are both at CalcChat. 41's at CalcChat. Any of the odds 43 through 55, they're all at CalcChat. 51's at CalcView. Any of the odds 57 to 61, they're all at CalcChat. 63 should be at CalcChat, and then you can explore doing 65 or 67 if you choose. That's completely up to you. 69, well, let's see, any of the odds 69 through 69 or 71 are both applied problems. I'll let you choose which are those. They should both be at CalcChat. You can think about doing 73 if you would like. I would suggest doing 75 or 77. They're both at CalcView, and so is 73. Should be, anyway. 79 and 81 should both be at Calc Chat. And then there's a true false, couple of them, 83 and 85. They should both be at Calc Chat. And then if you're really in the proofs, 87 through 93, I think all those odds are proofs, and they should be at Calc Chat. And 95 is in a little bit more complicated, interesting, however you want to call it, problem. You can take a look at that. If you'd like it, it should be at Calc Chat as well. Any questions? 4.2. All right, I take that as a no. So I'm going to get out of that, and unfortunately now your name's here. Well, that's not what I want. There we go. Have to close out this one. Oh no! Did I just lose everybody? Oh wait, I see. Okay, I've got you. I've got to start screen share again. So hold on and let me do that, and then I'll bring it back together. 4.3. Okay. All right, you got the screen again?
Yes.
Okay. And let me now do slideshow and go from current slide. All right. I'm going to move your names again. Hope you don't mind me pushing you around like this. Up here. Move you a little bit further. Okay. Let me move you a little bit more. There. All right. This is sort of frustrating. All right. We're still in Chapter 4, Application of Differentiation. We're now moving to 4.3, where we're going to be talking about increasing and decreasing functions and the first derivative test. Okay? And we're going to run into a lot of these little tests, so stand by for them. We're going to talk about the first derivative test here. Our objectives here are to determine the intervals on which a function is increasing or decreasing, and I hope some of you have some clues about what those would be, and we'll apply the first derivative test to find relative extrema of a function. Okay. Now, you might think, haven't we sort of done this before? And there's a sense that we sort of have, but not completely. And here's what we'll get to. Let's first talk about increasing and decreasing functions. Now, if any of you remember your Math 112, I'm sure you do, you will realize, yeah, we talked about this then. You may have even done it if you took Math 100 or in high school or whatever you did before that, but you certainly did it in 112 if you did Math 112. Okay? Well, we're going to do it from a calculus viewpoint now. Now, I hope some of you already are guessing what that's going to turn out being. I don't know if this is in your way, it's in my way, so I'm going to move things down here near the bottom. Yeah, that's a lot better. I'll have to move them later, I'm sure. This is, well, it's just going back and forth. You will learn how the derivatives can be used to classify relative extrema as either relative minima or relative maxima. We haven't gotten there yet, but we're close. First, it's important to define what we mean by increasing and decreasing functions. Okay. A function f is increasing on an interval when for any two numbers in the interval, x1 and x2, as long as x1 is less than x2, if you have those two numbers in that interval, x1 and x2, in that interval, x1 is less than x2, if your f of x1 is also less than f of x2, that means the function is increasing on that interval between those. at least between those 2 points. Okay? It's decreasing on that interval when for any numbers x1 and x2, where x1 is less than x2. But if your f of x1, the first one, at the lower end, is a greater value than your f of x2 at the higher end for x, that means that this is a decreasing function. And this is for any two x1s and x2s in that interval. So that's what we mean by increasing, decreasing. Or, like Jonah, you can do it on your graphing calculator and see where it's going up and where it's going down. That works too, but here is the analytic definition of what that means. Okay? So an increasing function is increasing when, as x moves from left to right, the graph is moving uphill. Okay? Like from here, let me get my pen set up again. If you're starting here and you're going in this direction, your f of x is always, f of any x to the right of this x is always greater than the f at that point. In other words, it's an increasing function. Okay? This one is decreasing as you're going because your f of x2 is less than your f of x1 if x1 is to the left of x2. Okay, that's a decreasing function. It could be something in between. That's a constant function if it's the same value everywhere in the interval. Now, got a question for you. Two questions in fact. This function you see in front of you here, is that a continuous function? Yay or nay?
Yes.
Yes. Is it a differentiable function?
Yes.
No, because your derivative coming down here is negative, there it's 0. Here it's 0, there it's positive. And this is an abrupt change that is not differentiable at x equal a or x equal b. Okay? So just so you can see that and remind you of that. So this function here between minus infinity and the point a, that is a decreasing function. It's constant between a and b, and it's increasing from b to positive infinity as long as it keeps going up like that. Now, here is what I hope you've already been thinking. Well, of course it's decreasing here because your first derivative is negative. The slopes of the tangent lines are negative everywhere here. That means it's a decreasing function. F prime of x everywhere on this interval from minus infinity to a is negative. Everywhere between a and b, the first derivative is 0 because it's a constant function. There is no change of y per change of x. Okay, slope is 0. Here, from b to positive infinity, the first derivative, the slope is always positive. So that's the other way. Your first derivative tells you whether the function is increasing, decreasing, or constant. Okay? Make sense?
Yes.
So, yeah, was there a question? No. Okay. As shown in theorem 4.5 below that's coming up, a positive derivative implies the function is increasing, negative derivative implies the function is decreasing, zero derivative on the entire interval implies that function is constant on that interval. And that's exactly what it says here. We just said it, they're saying it here, we just pictured it, they're saying it here. If f is a function that is continuous, got to be continuous on a closed interval a to b, and ours was, now we're putting in that it has to be differentiable on the open interval a to b. Now, that whole picture we saw before would not have been differentiable. A to b it was, because it was 0 everywhere in between. But now we're talking about in general. If f prime of x is positive, greater than 0, for all x's on that open interval a to b where it is differentiable, then f is increasing everywhere on the closed interval a to b. Okay? If f prime is negative, less than 0, for all the x's on the interval a to b, then f is decreasing everywhere on the closed interval a to b. And if f prime of x is equal to 0 for all the x's in the open interval a to b, then f is constant on that entire interval a to b. Okay? we knew that, right? Any questions? All right, here's example 1. By the way, flip the page over to page 222. Find the open intervals on which f of x is equal to x cubed minus 3/2 x squared, where the open intervals on which this is increasing and on which it's decreasing. How do you reckon we're going to do this? What's the Jesus answer? Take a derivative. F prime of x is equal to 3x squared. A little louder. Minus 3x. Perfect. Okay. Now, what you reckon we're going to do with that? Because what we're interested in is whether it's positive, negative, or 0. And we know what kind of function this is, right? Starts with P. Polynomial function. That means it's continuous where? Everywhere. And it means it's differentiable where? Everywhere. Okay, so we got all those bases covered. So we need to determine if it's if there are some intervals on which it's increasing or decreasing. Now, if it's continuous everywhere and differentiable everywhere, and if it's going to change its direction, that means it's got to have a derivative of what? Somewhere in between. 0. So let's first find where those critical values. Remember critical numbers, whichever the book calls it. How do we find those? Help me. Set it equal to 0. Those critical values occur where your first derivative is either 0 or does not exist. This is a polynomial function with a polynomial derivative. Its derivative exists everywhere. So we rule out that it does not exist. So let's find where that's equal to 0. How would we do that? I thought I heard someone whisper something. Factor, how does that factor? Help me. 3x times x minus 1. Perfect. Equals 0. What does that tell you? Either x equals 0 or I think I heard you say x equals 1. Perfect. Okay? So that gives us, that's an or there. That's a really ugly or, isn't it? I don't know what that looks like. It looks like an infinity sign. Who is it? Can't write. Okay, or. Okay, there we go. So, we know that we have a 0 derivative at x equals 0 and at x equals 1. So our point of contention here is what is it anywhere to the left of x equals 0. Okay? One thing you could do is pick a value to the left of x equals 0. Pick some value for x. Negative 1. Let's see what f prime of negative 1 is. Okay? And I think it's, well, either one's pretty easy. 3 times negative 1 squared minus 3 times negative 1. And what's that?
6.
Second? 6. 3 plus 3 equals 6. Yes. What does that tell you about the increasing or decreasing? Increasing. And where would it be increasing? Increasing from minus infinity to 0. Right? Okay. Now, I need to test it somewhere else, like between 0 and 1. Can anyone think of a value between 0 and 1? 0.5. Let's try that one. F prime of 0.5 would be 3 times, does anyone know what 0.5 squared is? 0.25 minus 3 times 0.5. Okay? Well, this will be 3/4. Can I just write it like that? And this would be minus 3/2. What does that come up being? I'm not really so interested in the numerical value. I want to know the sign value. It's negative. So this is decreasing from 0 to 1. All right. We need also then to have a test point somewhere to the right of 1. Anyone think of one? Anybody? 2. Okay, that sounds like a good one. So let's do f prime of 2. That would be 3 times 2 squared is 4 minus 3 times 2. And what's that?
6.
At least the sign of it. Positive. It's positive 6, by the way. Okay? And sure enough, so that means it's increasing also from 1 to positive infinity. Okay? So increasing from negative infinity to 0, decreasing from 0 to 1, and increasing again from 1 to positive infinity. But we kind of knew that, didn't we? Because we could look at this and see, this is, remember the good old leading term test for polynomials? If the exponent is odd, that means it's coming from opposite directions. When you go very negative, this is going to be very negative. When it's very positive, this will be very positive, that leading term. That tells you what the whole function is doing for very large negative numbers or very large negative numbers. So we knew it was coming from way down here in this direction and going way up here in that direction. Okay? So if we knew they had a first derivative of 0 at 0 and then another one, first derivative at 1 at 0, you knew it had to be doing this kind of stuff. Had to be. No way around it. It came from way down low, it wound up going way up high, and it had a direction change there. I say it had to. We do know it has to do that. There's just no other way it could do it. But sometimes you can't always guarantee it's going to change directions there. All you knew is it had a critical number there. That doesn't mean you had an absolute maximum or a relative maximum or minimum. If you remember back 4.1, which is a long time ago, we knew that was the case. Let's see how the book did it. They may have done it slightly differently than the way I did, but I think they probably did it pretty close to the same. First thing they do, know that it is differentiable on the entire real number line. Yep, we said that. And we did what the derivative was. And we got that as well. And then the next thing they did with that derivative was set it equal to 0 to determine the critical numbers. Okay? And that was at x equal, you factor, and they actually factored 3 out of the x minus 1. Well, 3 can never be 0. X could be 0 and x minus 1 could be 0 at x equal 1. So yeah, that's your your two values, x equals 0 and x equal 1. Those are your critical numbers. Okay? Because there are no points for which f prime doesn't exist, those are your only two critical numbers. Okay, because remember, those are the two criteria. Where the first derivative is 0 or where it doesn't exist. This is a polynomial function. It exists everywhere, so it's only where those first derivative is 0. Okay? So the table summarizes, and that's exactly what they're going to say, the testing in the three intervals, and they use the same values, well, almost the same values we did. Yeah, they did, the same values. x equal -1. That gave us a positive value. We know it's increasing everywhere from -infinity to 0. And from 0 to 1, it was decreasing the whole time because that was a -3/4. We didn't figure out what it was, but you probably saw that. It was negative. And then from 1 to infinity, at least at x equal 2, it was 6, and that's a positive number. It can't change again because there's no more critical numbers in between that, beyond that. So you know that has to be the case. So yeah, that's pretty much, they love the little tables. If you like the tables, write your tables, okay? Understood?
Yes.
Is there a question?
No, no question.
Okay, good deal. All right, so by theorem 4.5, f is increasing on the interval from -infinity to 0, and from 1 to infinity, decreasing on the interval 0 to 1. And here's is how that I didn't draw the axes in there, but you could have drawn those pretty easily as well. One really easy number is plug x equals 0, and you know 0, 0 is on that. You knew the first derivative was 0 there, and you knew it changed from increasing to decreasing. That has to be a maximum. At 1, it has to be a minimum, increasing beyond that. So you can plug in to the original function, x equal 1, and get the y value there. That'd be f of 1 is equal to 1 minus 3/2, which is minus 1/2. And that's how they got the y value there. Make sense? Any questions? Okay. Now, example 1 gives you one instance, I think. Gives you one instance for how to find intervals on which a function is increasing and decreasing. The guidelines below summarize these steps in that example. Okay, so what did we do? First, determine whether it's continuous or not on the interval. That's important. If it's not continuous, don't try to use any of these other things. It has to be continuous. Okay? Then, to find the open intervals on which it's increasing or decreasing, here are the steps. Find the critical numbers. Now, what are those? Tell me the two conditions for a critical numbers.
Equals to 0 or
First derivative equals to 0, or
does not exist.
first derivative does not exist. And notice up here, it was the f is continuous on that interval. It said nothing about differentiability. Okay? So you have to always consider, is there a value here where your first derivative doesn't exist? The function's continuous, but the first derivative is not defined. So those are the two things you look for. They give you the critical numbers. Now, here is a hint. Doesn't guarantee you that's going to be a place where it changes direction. Those are just your critical numbers. Those are the ones that you choose. It can only change directions at a critical number, but it doesn't guarantee it's going to change its direction at a critical number. So keep that in mind. So determine the sign of f prime at one test value in each interval, something to the right to the left of the least, and then in between each one of those critical numbers, and then to the right of the larger critical numbers. Determine the sign of f prime at each interval. Then use theorem 4.5 to determine whether it's increasing, decreasing at that. If that first derivative is positive, it's an increasing on that interval. If it's negative, it's decreasing. And if it happens to be 0 over an entire interval, that means it's constant. Okay? And then it says these guidelines are also valid when the interval a to b is replaced by an interval of the form -infinity to b, a to positive infinity, or even -infinity to positive infinity. Even though those aren't finite values, you can still do it. Any questions? Basically exactly what we did. All right. Here comes, oh yeah, bottom of page 222. A function is strictly monotonic. Now, what does the prefix mono mean? 1. Tonic, I don't know what it means besides something you take when you got a cold or something. No, it means where is it heading? Let's just put it that way. Strictly heading in one direction on an interval when it's either increasing on that entire interval or decreasing in the entire interval. Either one of those is monotonic. If it changes direction in the interval, it's not monotonic. For instance, the function f of x equal x cubed. Even though it looks like it almost comes to a stop there at 0, it doesn't. It's still increasing ever so slightly. If you picked a value very close to 0, like negative 0.1, okay, that's really close to 0, and cube that, you would have a negative 0.001. That's still negative, and if you went just to the right, like 0.1, that would be positive 0.001. So it doesn't actually stop. It goes up, it just decreases its slope very, very, very gradually. It does have a zero derivative there, okay? But then it keeps going in the same direction. It's increasing here, increasing here. The first derivative is positive on the left and positive on the right. So even though it's 0 right there, at 0, it's still strictly increasing, okay? It's a strictly monotonic over the entire number line because it's increasing over that whole thing, even though it slows down almost to a stop, but doesn't really stop at 0. Passes right through. Make sense? That's a monotonic function. All right. The function shown here is not strictly monotonic because even though it doesn't start decreasing, it is constant over part of that period. It's increasing from 0 to 1. From negative infinity to 0. It is constant 0 to 1 and then increasing afterward. That's not monotonic because it did actually stop increasing there and became constant. This is a piecewise defined function. You have to be very careful with those. It's continuous, and this one happens to be differentiable everywhere in that interval. However, it's not strictly monotonic because it doesn't increase the entire interval. Does that make sense? Okay. Let's see. I think we're ready then for the first derivative test. Okay. Didn't we already have? No, that was a different thing. Okay. After you have determined the intervals on which a function is increasing or decreasing, it is not difficult to locate the relative extreme of the function. Okay? For instance, in this figure here, we've seen that one before, haven't we? That's the same function we had before, example 1. It was increasing here, decreasing here, increasing there. Well, guess what? It changed directions at that point right there at 0, 0. That made it a relative maximum because it's increasing to the left, decreasing to the right, stand up, sit down. No. That's a relative maximum. Down here at x equal 1, it was decreasing coming into 1, increasing once it left 1. So right there is a relative minimum. Okay? That has a relative maximum at 0, 0 because it's increasing immediately to the left of that, decreasing immediately to the right, and it has a relative minimum at 1, negative 1/2 because it's decreasing to the left of it, increasing to the right of it. Okay. So if the first derivative changes sign at a critical value, you have a relative maximum or minimum, depending on what it changes from and to. If it's the same sign on either side, you don't have a relative maximum or minimum, even though it's a critical value, critical number. Similarly, f has a relative minimum at 1, I already said this one, at 1, negative 1/2, because f is decreasing immediately to the left of x equal 1, increasing immediately to the right of x equal 1. That means you have a relative minimum. Here's the theorem that states that. Okay? This is your first derivative test. Let C be, I'm going to move, I don't know if y'all can see this or not, but I'm moving the box up here. Okay. First derivative test. Let C be a critical number of the function f that is continuous on an open interval I containing C. So they've sort of reworded this, but it still means the same. First, f has to be continuous on an open interval I that contains... What's that again?
We're at time.
We're out of time. How can it be? You're right. Okay, we will pick up then. I could tell the sadness in your voice there, by the way. That was good to demonstrate. Let me see if we got any homework exercises in 4.3. I think we do, don't we? I think you can do example 3 on page 227. That should be at Calc Chat. I think you can do any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. And I think you can do any of the odds 11 through 21. They're all at Calc Chat. 13's at Calc View. We'll hold off because the next theorem was going to state the first derivative test. We'll hold off the rest of those until next time. All right, any questions? Good deal. It was good to see y'all. Did I get anyone else here besides JJ, Carlos, Jonah, Kyle, and Joanne? Anyone else come in the class? All right, good deal. We will see you on Wednesday. And look for it on Messages in Blackboard. And I'll give you codes there. All right, I've got to find, okay. Your names are in the way. I can't end the session. There we go. Stop share. We'll see you next time.
Bye, Mr. Felder.
Bye-bye. Bye-bye, Joanne.
Bye-bye, Dr. Colbert.
See you, JJ. All right. Ending the meeting.